In this video, I will be using spectra derived from NMR, IR, and mass spec to determine the structure of a selected unknown organic compound. So, IR gives the functional groups present in a molecule. It does this by measuring how molecules absorb infrared radiation and the vibrations in the molecules, typically focusing on bond stretching. Different functional groups absorb different characteristics of frequencies of IR radiation, and this is how I will be identifying the different groups. The x-axis of the spectra gives the stretching frequency, or the wave number, and the y-axis gives the amount of photons absorbed. So here is a chart giving IR absorptions and the types of vibrations of specific functional groups. As you will soon see on the IR spectra, I will be identifying these highlighted functional groups. By looking at the peaks and frequencies, the functional groups can be determined. The spectra is divided into 5 regions and a fingerprint region with specific groups appearing in each zone. Each zone has been mapped out below. From the chart in the last slide, a peak located around 600 to 800 is a carbon-chlorine stretch. A carbon-oxygen stretch in an ether is around 1000 to 1300, and a carbon-hydrogen stretch that is sp3 hybridized is typically within 2800 to 3000. The frequency here resembles a bend, but I'm mainly focusing on stretches. So from this IR spectra, I have found that it most likely contains an ether, an alkane, and an alkyl halide somewhere in the molecule. Further analyzing of more spectra will confirm this. Mass spec gives the molecular weight, degrees of unsaturation, and usually the chemical formula of a compound. The x-axis gives the mass-to-charge ratio, and the y-axis gives the relative abundance of an ion in the spectra. The base peak therefore has the longest peak, and the designated M+ peak gives the molecular weight. The smaller peaks are due to isotopes of atoms in the molecule. The peaks can tell you if there is a nitrogen, chlorine, or bromine atom present in the molecule. Here are examples of spectras identifying these 3 atoms. Organic compounds containing oxygen or halogens always have an even molecular weight. An odd molecular weight indicates that a nitrogen atom is present. A difference in peaks by N+2 signifies bromine or chlorine isotopes. To determine which one it is, look at the intensity ratios. An intensity ratio of 3:1 identifies chlorine isotopes, and a 1:1 intensity ratio identifies bromine isotopes. Here is the base peak, and here is most likely the molecular weight, since it appears to have a 3:1 intensity ratio, verifying that this molecule does have a chlorine atom. To find the molecular formula, subtract the atomic masses of electronegative atoms like chlorine and oxygen from the molecular weight first. Recall that the chlorine and oxygen were determined from the IR spectrum. This gives 43. Divide 43 by 12 to determine the number of possible carbons in the molecule, which turns out to be 3. What's left over is the number of hydrogens, since they each have an atomic mass of 1. So our molecular formula will be this. The degrees of unsaturation can also be calculated from this formula by plugging in N, the number of carbons. The saturated hydrocarbon would therefore be C3H8, giving this molecule no degrees of unsaturation and therefore no rings or pi bonds. Proton NMR is measured based on magnetic properties of hydrogen nuclei. The spectra gives the total number of hydrogens, the number of inequivalent hydrogens, and number of hydrogens attached at each different carbon, the number of hydrogen neighbors, and where in the molecule the hydrogens are located. This chart shows how counting the splitting of the peaks work. For example, if there's just one giant peak, this means that there are no hydrogen neighbors, and if there's 3 peaks, there are 2 hydrogen neighbors, and so on and so forth. This chart exhibits the proton's environment in the molecule based on its chemical shift, measured in parts per million, the ppm. This helps to determine the location of the protons within the molecule. Here is the proton NMR spectrum. Right away, it can be seen that the molecule has 7 hydrogens present, which was already determined from the mass spec spectrum. A closer view reveals that there are 3 different sets of hydrogens, therefore giving 3 signals. At each signal, the number of hydrogens given by the integration is attached to its own carbon. Since we are only allowed 3 carbons total in this molecule, the only possible C to H combinations are a CH3 here, a CH2 here, and another CH2. This gives 3 carbons and 7 hydrogens total, still corresponding to the molecular formula. Splitting shows that this peak is a singlet because it has one giant peak and no neighbors. A closer look here reveals 2 triplets because each one has 3 peaks total and therefore 2 neighbors apiece. When referring to the chemical shift chart from before, a 3.3 to 3.9 typically gives a CH2 oxygen bond, and a 3.6 to 3.8 gives a CH2 chlorine bond. This makes sense because when a group is attached to an electronegative atom, the chemical shift increases. Now the structure can be drawn. Recall the functional groups and formula above. We know that we must have a CH3 group at the end of a molecule with no neighboring hydrogens, as given by this peak. The only way to achieve this is by bonding it with an oxygen. Since chlorine can only have one bond, it must also be located at the end of this structure. What's left are 2 CH2 groups, each with 2 hydrogen neighbors. Therefore, if it is drawn like this, the desired number of neighbors are achieved. This proton has 2 neighboring hydrogens here. This proton has 2 neighboring hydrogens here. And this proton has no neighbors. This is the likely structure of this molecule. This can be verified with carbon NMR, which focuses on the magnetic properties of carbon-13 isotope nuclei. The carbon NMR gives the number of inequivalent carbons and their location in the molecule. And just as with proton NMR, when chemical shifts increase, electronegativity also increases. This chart shows the environment of a carbon relative to its chemical shift. The highlighted groups are present in my unknown structure. Here, there are 3 different carbons, as indicated here, here, and here. By looking at the values of the chemical shift, a peak at 50 to 90 is a CH2 oxygen bond resembling this carbon, and a peak from 30 to 60 represents a CH2 chlorine bond, which would be this peak. The remaining peak represents the carbon with 3 hydrogens attached, since it is the least electronegative and thus having the smallest chemical shift. In conclusion, when determining the structure of an unknown organic compound, spectroscopy instruments become extremely useful. IR can reveal the functional groups present. Mass spec can provide a chemical formula and a molecular weight. Proton NMR helps to determine the overall structure by giving the number of hydrogens at each signal and the relative number of hydrogen neighbors. And carbon NMR gives the number of inequivalent carbons within the molecule as well as their relative environment. By using spectroscopy, I have determined my unknown structure, 2-methoxyethyl chloride.